which means the second exam is going to be 1 week from today, next Wednesday. Yep. All right. All right. So you can find the practice exam, in the share folder. I just, move this one into the old X2 folder in the shared folder. And this one is CISP300-11 Okay, that's a wrong semester. So it should be 1183 for the spring semester this year. So it's just the previous semester, exam 2. All right. So this is the it's just a practice exam. There's no guarantee of how much your exam is going to resemble the practice exam. But it should show you the kind of question that I might ask, and also what topics will be included. Floating points is already done in exam 1, so I'm not going to have floating point questions in exam 2. So this is question number 1. Question 1 is about a bus contention. A bus contention is a situation where two components can drive the same individual wire, but in different directions at the same time. In other words, two ports are connected, but they want to specify different contents. While none of the TTP instructions causes a bus contention, it is possible with the current architecture. So in terms of the hardware, the connections, it is possible. It's just that all the microcode that I have specified are safe. But if I make a mistake in those microcode, then it is actually possible to cause a bus contention. Okay, so it's an issue with the schematic is potentially. Okay, so if I specify the microcode incorrectly, that can happen. In the following space, specify a microcode slice that can cause this to happen. Focus on the fields that causes the contention to happen. If a field is not important, mark it as question mark. Otherwise, a field should have a specific value. Okay, so the first thing we need to do is to figure out, okay, so what am I asking? Okay, so what is a bus contention in this case? So a bus contention is when you have two output ports that are trying to drive a wire in opposite directions. Okay, so I can give you an example in Logisim really quickly. So let me start a Logisim first. All right. So the quickest way to create a bus contention is just to use an input pin, hook it up to a NOT gate. So we just get a NOT gate here, and then have the input pin to connect both to the input of the NOT gate and also to the output of the NOT gate. Now, instead of making the connection right away, I just want to do it like this before they connect. So you can see the output of the NOT gate is a 1 because the input is a 0. But if I connect the 0 that is going into the NOT gate with the output of the NOT gate, then we have a bus contention, because the input pin is trying to drive that wire to a low state, but the output of the NOT gate is trying to drive the same wire to a high state. So that's why we have a problem like that. So this is a bus contention. So now the question is, in the processor, where is the potential place for bus contention? There's one. Okay. So this only happens when both ports can be configured as output and they are connected. If one port can only be input, the other one can only be output, not a problem. If both can only configure it as input, not a problem. If one component is not driving, it's sleeping, okay, it's not paying attention at all, not a problem. So the question is now, basically, how familiar are you with the schematic of the processor? So using the poking tool, that's really helpful. So you can see, you can look at any particular wire and ask, is there potentially a problem? This is not a problem because it's connecting the output of a demultiplexer to the input of a multiplexer. So only one can drive the wire, and the other one is just sensing. So it's not a problem. So you have to look at two components that can drive the same wire at the same time. They can both be in output mode at exactly the same time. Okay. So now you have to think about, well, if that is the case, okay, if two components can both be output at the same time, we probably will have a lot of problems with this design to begin with. So the potential problem has to be something that can be both input or output, okay, because sometimes it's input, sometimes it's output. It is just by using the correct bit patterns in the microcode sizes that they do not become output at exactly the same time. So it's controlled. So now you have to ask yourself, which component or components has a programmable output? Sometimes it is an output, and other times it is not an output. So we go through some of these devices and try to figure out which one can meet that requirement. This is one of those. So with a demultiplexer, with this one, it has an enable, which means the output sometimes can be enabled, other times it can be disabled. So you look at this wire, it's not a problem. You look at this wire, it is not a problem. And then you look at the last wire, well, that potentially can be a problem. And then you have to look at where it connects to. Okay. So it connects to the data bus. So that means this particular demultiplexer can be configured as an output. But remember, in RAM, if you specify a read operation, it is also in output mode. So there is the problem. Okay, so these two potentially can cause a problem. It depends on how I specify the bits. So if I specify RAM cell, so that when RAM is selected, RAM load being a 1, which means we're in a read configuration, and also at the same time specify RO0EN to be a 1, then we can potentially have a problem. So that's basically is how we can end up with a bus contention. And the specification in this case, so to answer the question, so the specification is the microcode pointer select, doesn't really matter. So you can put a question mark here. PCEN can be anything, it doesn't really matter. PC mux can be anything. Address mux can be anything. ALU OP can be anything. ALU EN can be anything. And by the way, these are the names of the tunnels. Okay, so if you go back to the schematic, those names are referring to exactly the names of the tunnels. So we basically put question marks in everything except for this one here. So this one has to be a 1, and then the RAM also has to be specified. RAM load has to be a 1. RAM cell also has to be a 1. So when we have 3 1s in this particular picture, everything else can be question marks. Okay, they do not really matter. But if we have 3 1s here, then we can end up with a bus contention. So obviously, I'm not going to ask exactly the same question again, but I will ask another question that requires you, well, that will let you demonstrate your understanding of the schematic, in your answer. So it's the same kind of deal, except, it's not going to be the same question. Are there any questions about number 1? We're talking about a test, exam 2 on next Wednesday. So how do you study to prepare for questions like this? Yep. You can mark it up. Yep. Well, the first thing I would do is really just to go through the entire processor architecture, look at every component by itself, and ask myself, do I understand how it works? Okay, what does it do, and what the ports really mean in a multiplexer like this? Now there are different types of multiplexers, by the way. This one does not have an enable, so it's always enabled. Okay, whatever you select using this wire is connecting one of the inputs to the output, but the output is always driving. Okay, we look at the RAM component. Do we understand how the RAM component operates? Okay, what is the meaning of the A port? What is the meaning of the cell port, and so on? So you have to understand each component by itself, and feel really comfortable first. Then we can go into something that's a little bit more complex, like a register. A register, even though it is a quote-unquote small device, it has a lot of ports, right? It has a D port, it has an enable port, it has a clock, it has a reset port, and it has a Q, which is the output port. So you have to understand how those ports are used and how they can specify the behavior of a register. Let's see, what else? What other components do we use? Well, we have an AND gate here, but this AND gate has a negated input for this particular wire, so you have to understand how that works. And then inside the processor bank or the register bank, we have a decoder. So you have to look at the decoder and say, do I understand what a decoder is and what does it do? And this particular decoder has an enable. This is the enable pin of the decoder. What does it do? What happens when the enable of the decoder is 0? What happens when the enable of the decoder is a 1? Okay, so those are the individual components. You have to make sure that you understand the operation of each individual component first. Okay, I don't think we have any other major component other than the splitter. So I'm assuming that is not an issue because we just have to understand how a splitter. There's one major one here, and then there's another major one here. There's another one up there, with the flags register. But basically, a splitter just splits a thicker wire and splices it into smaller wires. But each smaller wire is not necessarily just one bit. It can be a bundle of bits. But the bundle of bits is specified here. Okay, like this one here specifies it is bit 8, bit 7, and 8, bundled into one single wire. This one here is 3 bits. It's bit 13, 14, and 15 bundled into ALU OP, which is the ALU operation specification. Okay. As individual components, there are a little bit more inside the ALU or the arithmetic logic unit. So when you look into the ALU, we have a multiplexer, but this multiplexer is a little bit different because it also has an enable pin, which the other multiplexers do not use. Okay, so you have to understand what that is going to do. We have a NOR gate here. Let's see, we have a bit shifter, and then we have a subtractor and adder. This is a bitwise NOT, bitwise AND, bitwise OR. There's a whole bunch of gates here for computing the overflow. Depending on whether you're adding or subtracting, that appropriate one is going to the output of the overflow flag. And then we have an exclusive OR gate here to compute the L flag based on the sign and the overflow flags. So I'm just highlighting, some of the components that are kind of unique in this design. They're all, there are registers all over the place. I mean, so there's not really a whole lot to say about, registers. So that will be the first stage, okay, of studying, is to make sure that I understand every single component. Okay. Now, if I say, well, I really understand the component at this point, but during the test, maybe I need to refer to some reference material. Remember how you can extract the HTML documents out of the help file? Okay, so you just find out all the registers, multiplexer, demultiplexer, decoder, register, RAM, ROM, okay, and print those out, okay? So print it out, with a little sticky on the side, so it's easy to find which one is which one, okay? So that addresses the first layer of concern, is do we understand the components? So the next one is to say, okay, now that I understand each individual component, what can I do to understand the processor itself? In other words, the interaction between the components. That one, you really have to study the microcode of instructions. Okay, so that's pretty much the the best way to do it. So I'll give you a list of instructions that are particularly important. So even though there are, I think 20-something instructions, there are certain ones that are really close and they do about the same thing, so you don't have to study all variations of that. So the first one is no op. Okay, you have to understand how no op operates. No op is really just fetch and decode, and then it decodes back into location 000 to get the next operation. So it doesn't really have anything really useful to do, but it does have fetch and decode in it. Halt is kind of interesting. It does have the fetch cycle, the decode cycle, and it does have 0, 1, 0 in ROM, that location corresponding to how the internals of the processor should be wired. But then once you get there, it doesn't go anywhere else. Okay, so the halt instruction is kind of special in that way. And then we have all the instructions that can copy things around. There are 3 instructions that will do that. There's the LD instruction, the LDI instruction, and then there's the ST instruction. So with each one, just pick one specific one to look into, okay? And then you just program that code into the RAM, and then see how the pathways are established, in the processor. So with LD, you can just do something like this, okay? Doesn't really matter what it is. LDI, you can try something like this, okay? And then with ST, you can try something like this, okay? So try to hand assemble the opcode and then program that into the RAM component of the processor, or you can just inject that code into the microcode pointer to go to that location. Then you can examine and poke around the wires and figure out what the processor is going to do. So these 3 belong to one single family because they are only here to copy stuff around. And the last one, which I kind of don't talk about a whole lot because it's really easy. This one is just copying a register to another register. So in this case, it is copying the content of C to B. It doesn't do any dereferencing. It does not access RAM at all. It is really just copying between registers. Okay, so I would look into these. If you want to look into the complexity, I would say CPR is the easiest. So look into that one first. So look at CPR, BC, and then the other ones. So that is one whole family of instructions. And then the next one, I would say JMP. JMP, B, with a particular register, and then JMPI with a certain location. Doesn't matter what that location is. You just have to say, okay, what does that do, okay? And how does it get it done? So these 2 are unconditional branches. And then conditional branches, you can just do a JCI. Same thing, B, and then JC, B, and then a JCI to location 25. So with these 2, they are conditional branches, which means you have to either set or clear the carry bit in order to find out what they're going to do. So to test these 2 instructions, I can give you an idea of how to do it in just a moment. And then you have a whole bunch that perform calculations. So those would be like add instructions, subtract instructions, and stuff like that. So you have add AB, which will perform the addition between A and B, and then A, whatever is on the left-hand side or the first operand, will store the result of the 2. So add, subtract, compare are pretty much the same thing, except compare does not store the result back into the first operand. And then you have and, or, okay, those are bitwise operations, but otherwise they are going through the ALU just the same, okay? And then you have not, which only requires one single operand because it's a unary operator. And then you have shift. Shift has to get rid of some of the bits of the second operand because you can only shift up to 8 bits. And to specify a number up to 7, you only need 3 bits. So that one is kind of special in that way. But all the differences can be seen within the ALU design itself. Okay? Let's see, what else? Oh, we have increment and decrement. So increment and decrement are about the same, The only difference is one is increasing the value of a register by 1, and the other one is decreasing the register by 1. So you might think, but why are we not lumping increment and decrement into add? Well, that's because increment and decrement, they do not change the flags register. So even though we push content through the ALU, the flags register is not affected by the increment or the decrement instruction. So you might want to look into that to figure out how it gets that job done. How can we push something through the ALU and yet it doesn't affect the flags register? Okay. I'm just going through my mind here. I think that's it. These are all the instructions that are very representative. Each one is representing an entire family of instructions or opcodes. So what you want to do is to go through the whole process and say, do I know how to assemble these things by myself, by hand? Okay. We'll just pick a random example. We'll just pick this one here. Do we know how to assemble it by hand? So you look up the so you have to look up the opcode table. That would be the most concise way to look for that. So go to shared. Oh, by the way, anything within the shared subfolder, you can view those documents, you can print those documents, you can bring those documents with you to the exam. So anything you feel, oh, this might be handy, well, print it out and bring it with you. So we go to the opcode table, and then the instruction that was in question was which one? I can't remember what it was. JCI, okay. So you look up JCI, okay, so JCI is right here. So the JCI instruction has an opcode of 44, okay, just exactly 44. It doesn't have any XXYY because it doesn't use a register, but it has one extra byte. The extra byte is used because in case the carry flag is set, whatever the program counter is pointing to when the instruction, when the opcode executes, is going to be used to load the program counter. So that is the important part. So you have to, so this instruction is a little bit tricky to test. So you have to say 44, and then whatever number or label is next to it is just that number. So that means to assemble this particular instruction, it is really literally 44 in hexadecimal, and then 25 in decimal, because the assembler cannot take in hexadecimal numbers. The assembler can only take in decimal numbers. Is that okay? All right, so given that is the case, okay, how do we gain a better understanding of the JCI instruction? You can always just write a very short program, assemble it, load it into the processor, and then single clock the whole thing, and then just observe the wires as it executes. But there's a much easier way to cheat the whole thing. Okay, so I'm going to teach you guys how to cheat it. So you go to the assembler, the simulator, and then the way you do it is just change the microcode pointer. What was the opcode of JCI again? 44 in hexadecimal. So I'm just going to change the microcode pointer to, well, yeah, that'll work. So I'm going to change this one to 440 because it is the opcode plus 1 0 for the least significant hexadecimal digit. So this is the slice corresponding to JCI itself. Okay, so now you have to look at all the stuff that is going on in the processor. Now, because it's also a conditional branch instruction, that means the state of the flags register is important. If the carry flag is a 0, the instruction would do one thing. If the carry flag is a 1, the instruction would do something else. So that means what you need to do now is to go to the flags register and say the carry flag, I think is, I cannot remember the bit number. Let me look it up. The reason why I do not remember all of this stuff here is because I can always look it up. Anything that I can look up, I do not remember. So that's a lot of stuff. So you can see cout is bit 0 of flags out. So that means you can now, you can now go back to main, go to the flags register, and then change bit 0 of the flags register to a 1. Okay, so as it is right, this is the instruction register. Need to move up a little bit more. So as it is right now, the carry flag is a 0. So you can now go take a look at, okay, if the carry flag is a 0, how is it affecting the program counter? Because JCI is going to update the program counter regardless, one way or another. But it updates the program counter differently depending on whether the flag is a 0 or 1. So right now the flag is a 0, so you have to kind of go through all the computation, look at your PC mux, look at PC mux, and then go back here and look at everything that can affect the program counter and say, oh, if the flag is a 0, then the program counter will simply be incremented. Okay. How do I know the program counter is going to be incremented? Well, you just have to look at how are we updating the program counter? Yes. Okay. How are we updating the program counter? The multiplexer has a select of 0, which means we're taking input 0 of the multiplexer to the output. That's coming in from the adder. The adder is definitely adding 1 because the carry in is an OR between PC inc, program counter increment, and address mux, and address mux is a 1 at this point. So we are just adding 1 to the program counter. The program counter is added, is incremented again with this particular slice down there of microcode. So the next question is, but what if the carry flag is a 1 and we're supposed to branch? What is going to happen then? Well, then you go to the flags register and force a 1 into that position. So 0, 1, because the carry flag is bit 0. So, that's why I put a 1 into the flags register to basically inject a 1 into the carry flag. So in that case, you can look up, how the program counter is going to be updated. So this is the program counter. It's going to be updated by this wire. But the multiplexer now has a 1 as a selection, which means it's taking input 1 to update the program counter. And that in return is coming from another multiplexer. This multiplexer here is controlled by this AND gate. And with this particular AND gate, PC mux is a 1 at this point. Register output 0 enable is a 0. That's coming. This one is coming straight out of the ROM. This one is actually computed. So with this one here, we know that we need to look up this wire. That wire goes all the way to RAM, and the RAM is selected, and it is also being read at this point. So, but what location are we reading from? Who is dictating that location? We can see it's location 0, 0, but don't be tricked by that one. Okay, because what we need to do now is to figure out what is driving the address port of RAM. Okay, it is coming from the multiplexer. This multiplexer has a selection of 1, and the selection of 1 means input 1 of the multiplexer becomes the output of the multiplexer. So input 1 is coming from, guess what? The program counter itself. So this is what I want you to kind of go through to study those instructions. This is probably by far the most complicated instruction to track, because it's conditional. There are 2 alternatives that you have to individually track to understand the instruction. The other one, like CPR, is like super duper easy. Okay, everything is turned off except for the register bank. One output is turned on, the input is turned on, and then 2 bits select which register is the output, 2 bits select which register is going to be updated, done. So that one is easy. This is by far the most complicated one. So that is how I would study and gain an understanding of how the processor operates. Okay? And as you go through this exercise, okay, you cannot bring Logisim with you during the exam, but you can bring any amount of printed or handwritten material with you. So if you go through for each of these instructions, okay, make a new copy of the processor architecture. Highlight the wires that are going to be active. Highlight the registers that are going to be active. Then you have one pictorial or graphical explanation of that particular instruction. So you end up with how many sheets? I don't think you will need a paper for no op or halt, okay? So for the rest, you're just talking about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the conditionals, you need one for the 0 and one for the 1. So you have 12 sheets of paper that you need to bring with you. But the process of making those pieces of paper is studying. And if you make your own annotation, I really doubt that you will need that many pieces of paper during the exam. On the other hand, if someone says, well, I know that person is going to have the best preparation for the test, and I'll just ask that person to make a photocopy of everything so that I also have that same material in the exam, then I'm going to be screwed. Because I have no idea how the content of all that material gets generated, because that's just printed. It's not reminding me of something that I have personally investigated and understood. Okay? But you guys can decide how you want to do it. The entire class can sit down together and come up with a pile of paper that you guys think would be helpful. Okay, that's as long as it's done before and not during the test. It's okay, not a problem. So are we doing okay so far with how to really understand the instructions, because that's what the test is going to be testing you for. Okay. Now the test is on next Wednesday, which means if you go home over the weekend and go like, okay, I'm going through all of this stuff here. Oh, Monday's a holiday, is it? Darn it. Okay. So I'm going to be on duty on Monday in case you guys have questions. So I will answer questions on Monday, but online. I won't be here on campus. Okay. But anyway, if you have any questions, after when you study, I will answer those questions. If it's a complicated, kind of question, and I say, well, that's a legitimate question, I'm going to answer that. I might even, make a short YouTube clip to answer that question. But if I do something like that, I will probably post it to the entire class. So are we okay so far in terms of, how to study for the instruction set? Okay. All right, so the next thing, I think it's kind of important. It really should not be an issue at this point, but just in case it is, there are several terms that, that I use kind of in similar ways, but they're not exactly the same. So there's the term of instruction. There's a term of mnemonic, M-N-E-M-O-N-I-C. I think I have a spelling mistake here. Mnemonic. I think that's right. Okay. There is the term of opcode, okay, and then there's a term of microcode. So what are these things? Okay, how are they the same? How are they related? Instruction is kind of interchangeable. Sometimes I use instruction to refer to mnemonic, which is the symbolic name of stuff that we use. So in this case, let me just give you an example. JCI 25 is a mnemonic, okay, because the computer really does not understand, the toy processor really does not understand what is JCI. JCI as ASCII codes, J, C, and I, has no meaning whatsoever to the processor. But the opcode does. So the opcode in this case is 44 in hexadecimal, which really is just a fancy way or a more compact way to spell out the binary bit pattern of 0100, 0100 in base 2. Same thing, just different representation. That's the actual opcode. The 25 is not really technically a part of the opcode. It is the byte after the opcode, but it is needed in order for the instruction to execute. Okay. And then the last one is microcode. The microcode is whatever is at ROM location. In this case, 440. Okay, that's the first slice. Okay, this is the first slice of microcode corresponding to JCI. Okay, so that's kind of how things are related. Is the microcode dictates how the components are connected. The opcode is really just a binary bit pattern that says Oh, go to that page of microcode, and that will tell you how things are supposed to be connected within the processor. But it's difficult to remember, okay? 0, 1, 0, 0, 0, 1, 0, 0 is kind of hard to remember and associated with conditional branch based on the carry flag, right? So that's why we have mnemonic, which is easier to remember from our perspective. And then the assembler translates JCI 25 to this bit pattern. And then if you want 25 also as a bit pattern, we can do that too. So 25 as a bit pattern is going to be 0001, which takes care of a 16, and then 1001 to take care of a 9. So that is in base 2. So the 2 bytes corresponding to this particular mnemonic is going to be 010000100 as the first byte, and then the second byte is, oh, I think I'm missing 1 bit here. There we go. So the second byte is 00011001. Those 2 bytes, is what the assembler is going to spit out when you say JCI 25 in the source tab of the assembler. Okay? When this opcode executes, okay, not counting the fetch nor the decode, by the time the actual microcode executes at location 440 in hexadecimal in the ROM, that is what is actually dictating the components, the behavior of all the components inside the processor. And that really is the bottom line. I mean, there's no better way to explain how an instruction executes than just looking at the processor and find out how the components are connected because of the microcode. Is that okay? Cool. Okay, so this is one part of the exam. It's really just to test whether you understand all of these things thoroughly. And then the second part, okay, so let me get back to the practice test here. So the second part, okay, where's my practice test? Oh, right here. So the second part is basically testing, do you know how to put instructions together to perform specific operations in C and C++. Last year or last semester, I did not include subroutines or any concepts related to subroutine in the second exam, so I'm going to do the same thing this semester. So no subroutines nor stack operations in exam 2. Yay! Well, that only means that stuff is going to be heavy duty in the final exam. Oh. Okay, so I'll give you code like this, okay? This is an example where, A, B, C, D are registers, okay? So there's no need to use memory whatsoever. They're all in registers already in this particular example. And I'm just asking you to translate it into assembly code. That's all. So what you need to do, okay, if you want to go through the step-by-step process of, flattening first and then converting the comparison and stuff like that, that's fine, okay? If you want to just kind of eyeball this and go like, yeah, I can do it, without, flattening first, that's fine too. So whatever you do, you just have to make sure that your assembly code reflects the behavior of the C code. So I'm going to give you the solution of this one and also kind of demonstrate, how to approach this kind of question. Okay. So if you plan to use like a full procedure of flattening and stuff like that, you might need extra sheets of paper. So you have to bring your own extra pieces of paper because I don't have any extra supply. All right. So in this case, I'm just going to do the translation kind of without going through very much step-by-step process. The difficult part is something I can do with an editor is really hard to do it on a piece of paper. So you might need to do a lot of like insert symbols, which is okay with me. Let me show you what I mean by insert symbols, because that's something that you might want to do just because it makes sense to me, and I would imagine that it makes sense to some of you. It's harder to do when you're using a piece of paper. Are there any questions at this point about the practice exam, how to study, what kind of material will be in it? So yeah, go ahead.
Will we have anything on the D flip-flop?
No. Yeah. So the D flip-flop is really just to help us get to registers, but registers definitely will be. I would assume that you understand what a register is and how it operates. Okay. All right. So getting to the tablet. Screen copy. There we go. And you can see the temperature of the processor, when it hits 80 degrees right here. Oh, it's already at that temperature range. So now the clock speed is going to be governed. It's going to say, okay, let's reduce the clock speed because it's getting hot. The processor is getting hot. Okay, so so in this particular question, okay, so I'm going to write the answer to this question as if it is on the piece of paper. So question is here, and this is potentially how you can write your answer. So I might do something like this. Okay, C gets 0. There are two ways to do it, but the most obvious way is just LDI C0. Okay, that's fine. Cool, easy. The second one is a while loop, and I already know the structure of a while loop. Okay, I will need a label to indicate the beginning of the while. So I have while begin here. And there's a label definition. That's why I need a colon. And then I need to test the condition, which means as long as D is less than 20, we want to stay in the loop. But as soon as D is not less than 20, which is greater than or equal to 20, we want to get out of the loop. So in my mind, I can do this translation kind of right away. So I can just say now, let's put D into let's put 0 into register A, which is kind of like a scratch register. It's not used anywhere else in this code, so I can use it. And then we'll compare that to D. Oh, excuse me, this is 20. Okay, so load A with 20. And I want to compare it in a way that is easy for me to figure out what to do with it. In reality, either way of comparison is okay. It's just affecting how you do the branching. Okay, so I'm just going to do a compare. Well, since the original code is comparing D to 20, I'm just going to do it like this. But if you do it like this, then you have to say, well, what are the flags indicating at this point? I think in the test, does anyone remember whether they're signed or unsigned? I cannot remember, so let's check. They're assumed unsigned. Okay, so they're assumed unsigned. So now I have to D minus A is D minus 20. Okay, so we are comparing D against 20. The conditional branches that they can use are equal to. So let's take care of equal to first. Okay, because when they do equal, I need to get out. So we'll just go ahead and do a JZI to while end. And I'm just going to put while end here. In other words, this is me writing this on a piece of paper. So I would just put while end, but leave enough space because I know I might need some more space here. If they're not equal, then we have two choices because it's either less than or greater than. If D is less than 20, we're staying in the loop. Okay, so that means, but that's the only conditional branch I can use. So in this case, it's JCI, and we'll just say while body, and then we have a JMPI to while end. This is a little bit more clumsy than it needs to be, but it also shows that you can do it in this way too. Okay, so it's kind of cumbersome because JCI is saying D is actually less than A and A is 20. So if D is less than 20, we branch to while body, which is this label. And then if we get to this JMPI instruction, that means D is not less than A, and D does not equal to 20, which means it's greater than 20, so we should get out. So that's why we have a JMPI to while end. There's one more thing, okay? Because at the end of a conditional branch, at the end of a while loop, I need an unconditional branch JMPI back to while begin. Oops. Okay, because that's how we complete the loop. So that takes care of the loop structure itself without anything inside the loop. So what do I do? Well, this is what I say. This is what I'm referring to as inserting content. So you basically say, okay, this big chunk of code goes in between while body and JMPI while begin. So that way you can kind of focus on the structure of the code one level at a time without thinking, oh, but I need to remember to have an unconditional branch back to the beginning. Well, do it right away while you're focusing on just that control structure, okay? So now that we have the while loop control structure done, I can now really focus on just the inside of the while loop, okay? So inside of the while loop, we have a conditional statement. And the conditional statement says, if C and 1, okay, so we'll have to figure out how do we do a bitwise AND, okay? So the bitwise AND, we need LDIA 1 in this case because the bit mask of 1 needs to be in a register. So now the next thing we need to do is to do an AND. But now you have to be careful because which register do you want to overwrite, okay? AND is going to overwrite the first operand. So if you say AND DA, then it's going to overwrite register, if you say AND CA, it's going to overwrite register C. But the C code doesn't say anything about overwriting register C at this point, okay? Register C is supposed to be incremented later on, but we are not going to do a bitwise AND and store the result of the bitwise AND into C. So you have to be careful and only destroy the scratch register, which is not represented anywhere in the C code. Like that. All right. So in the C code, okay, implicitly, it is saying, it's really asking, is C bitwise AND 1 not 0? That's basically what it really was asking. So you might say, oh, so we need to compare that to 0. You don't. Because the AND operation, the result of any operation through the ALU, with the only exception of the increment and the decrement instructions, they all set the sign flag and also the Z flag. And the Z flag will tell me whether the result is 0 or not. So I just have to do a JZI. Okay. So if the result is 0, we go to the else label. So we specify the else label here. And this is the kind of difficult part because you kind of have to estimate how much code is in between if you want to truly use the structured code approach. Okay. And then this has to jump around JMPI around the else branch, so it has to go to end if as a label, and then end if is going to be at the end here. Now, of course, if you do run out of space because you took care of the control structure, but there's not enough space here, you can always just put 2 more insert symbol here, so I can say, oh, okay, that chunk of code goes in here, that chunk of code goes in here. So that's perfectly okay. In fact, I'm just going to do it now. Okay, so now I say, okay, this piece of code goes in here. Okay, that's the then branch. So when you look at the C code, the then branch is just adding 2 to D. There are many ways to do it. You can load A with 2, do an add DA, that works. But you can also just say increment D twice. That works the same way, okay? The other one is the else branch. The else branch, according to the C code, is only adding 1 to D. So that's only one single increment, like so, okay? But don't forget the last one, which is an increment of register C. So you kind of have to, okay, so we have to erase this and say the last instruction within the while loop is a simple increment C to finish that line of the C code. So this would be perfectly acceptable as an answer. And it helps to avoid the problem of, oh, I didn't plan enough space, I ran out of space in between the control structure, jumps. Well, just use this symbol. Tell me exactly where this is supposed to go. As long as that part is clear, it's fine. So is that okay? Yep. You mean here? Because I need to bitwise AND with C. A is not a counter. A is a scratch register. That's all it is. Okay, so now the question is, what if somebody says AND A, comma 1? Well, that would get some deduction, okay, because that instruction does not exist. So you have to understand what modes are supported by instructions. There are only very few instructions that has an immediate, component. So any instruction that ends with an I can specify an immediate. LDI, JMPI, JCI, JZI, that whole family, that's about it. Everything else can only work with registers. Add can only work with registers. Subtract only work registers. Compare only registers, and so on. Okay? So if someone gives me the right idea but the wrong opcode, which does not exist, I will still take points off. Because if you study the architecture itself, it is pretty clear that the AND instruction cannot take an immediate operand. In fact, no ALU operations can take an immediate operand. So is that okay? All right. So what if somebody forgot about this JMPI to while begin, at the end of the body of the while? That would be a deduction too. Maybe not a whole lot, but there will be a deduction because it is actually very important for a loop to go back to the beginning. Now, what if somebody has this JMPI instruction, but without the label definition at the beginning of the loop? Minor deduction, I would count it as as oversight, just being careless, okay? Because it would actually receive less deduction compared to missing the jump instruction altogether. Because JMPI to loop to while begin kind of indicates that person knows that it has to go back to the beginning, but without the label definition, I cannot tell where that person wants to jump back to, so there will still be a deduction. What if someone spells while begin with an uppercase B here and a lowercase b over here? No deduction in that case, but because the assembler is actually case insensitive. So, but any obvious typo is not going to be a problem. Okay. The only exception when the typo would actually matter is JMP versus JMPI, okay? Because that I is really significant. So don't miss an I or add an I when you don't need it. So is that okay? All right. So that's question number 2. Here's question number 3. So question number 3, I think the answer is already there too. Assume that registers A, B, and C A, B, C, and D are initialized to the last 4 digits of your student ID, so each person has a slightly piece of code now. If your student ID is 1, 2, 3, 4, 5, 6, 7, highlighting the last 4 digits, then assume register A has 4, register B has 5, and so on. There's no signedness inherent to the registers. Execute the following code by hand and write down the sequence of rows. Each row starts with the line number corresponding to the instruction executed. The line number is followed by the values of all registers reflecting the value in unsigned decimal representation of each register after the line executes, blah, 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 blah. So I'm just asking you to do the trace. So instead of having Logisim to do the log, you are doing the log by hand now. Okay? It is not as painful as it seems. Because most people look at this and go like, oh, that is going to be quite painful. Nah, not too painful. So I'm going to do it on the side using my tablet. Okay, where's my tablet? Oh, I just passed it. There we go. All right. So I'm just going to assume it is the student ID is 4567, okay, with those particular registers. So I'm just going to write down here. Yep, okay. I'm just writing down on this side here, then I can start. 4, B equals 5, C equals 6, D equals 7. But this year, I'm not going to do it the same way, because last year some student had, different students have different digits in the student ID. So one student had a trace about this long, another student only had a trace about this long. So this year I'm going to do it slightly differently so that there's no fairness issue with that. Okay. All right, so this is the initial condition. So the first line is line 2, okay? So in your answer, you have to say, line 2. And of course, the compare is not going to change any of the registers. So they all remain the same. A is 4, B is 5, C is 6, D is 7. But then you also have to indicate the result of the comparison, because that's what is important for the branching. So since we are subtracting 5 from 4, okay, so you kind of have to make sure that you understand how the flags are going to work, okay? So the C flag, the carry flag is going to be a 1. The Z flag is going to be a 0. The sign flag is going to be a 1. Overflow flag is going to be a 0. And then the L flag is also going to be a 1. Because the conditional statement, the conditional branch requires that you know how the flags operate. So when we get to line 3, we can say, well, there's really no change to the registers, but we are doing a branch, okay? So if there's no change to the registers, you can just kind of use this symbol to say that they're the same as the previous line. But then you also want to kind of comment and say, jump to label L2. So when you jump to label L2, then execution continues on line 8. Okay. So on line 8, we're incrementing A. So A is now 5. The rest are the same. And then after line 8, we go to line 9. Line 9 doesn't do a single thing to the register, so they all remain the same. But we are changing the execution path back to label L1. So now we're back to label L1, which is on line 2. So now we're comparing 5 to 5. So when you compare 5 to 5, then C is going to be cleared. Carry flag is cleared. The Z flag is a 1. Sign flag is going to be cleared. Overflow is going to be cleared. The L flag is also going to be cleared. Then we go to line 3, which is the next line. JCI is not going to branch. So no branching here, no jump. Line 4 is JCI to L3. So this one does branch. No register is changed, but we are branching. So we are jumping to label L3. Then you go down to label L3. Where's L3 defined? Right here. So L3 is, so line 11 is the next one. So we compare CD this time. So CD is 6 and 7. So no change to the registers, but you have to indicate that the carry flag is going to be a 1. The 0 flag is going to be 0. Sign flag is going to be a 1. Overflow flag is going to be a 0. L flag is going to be a 1, because we are subtracting 6 from 5. And then we have line 12 is JSI. No change to the registers, but we are branching because the sign flag is a 1, so we are branching to L4. And then L4 is down here. And then we get to line 17. Line 17 is an OR. This is a bitwise OR between C and D. Register C is 6, register D is 7. So now the question is, do you know how to do a bitwise OR? Spell out both of those in binary and then do a vertical OR, for each column. Okay? You can do it on the side. Okay? So we have 6 being 0, 0, 0, 0, 0, 1, 1, 0, that's 6. And then 0, 0, 0, 0, 0, 1, 1, 1. Oops, you cannot see it. That's 7. So you're now doing a bitwise OR. So the result is 0 or 1 is 1, 1 or 1 is 1, 1 or 1 is 1, the rest are all zeros. So we'll still put a 7 here and say that D is 7, even though it is not changed from what it was, but there is an operation. The next one is bitwise NOT with register C on line 18. So now we have to look at register C. Register C has a value of 6. So we are looking at 0, 0, 0, 0, 0, 1, 1, 0, and we want to take the bitwise NOT of this thing. So it ends up with 1, 1, 1, 1, 1, 0, 0, 1. So that's going to be in register C. Unless you want to do the conversion to unsigned number representation, you can probably use hexadecimal, easier to deal with. So this is F9. So D is still 7. And then where do we go? Halt. Okay, well, we get to line 19. A halt, which does not change any one of the registers, and we're done. Yep.
On line 17, did it overwrite C with the result of the OR?
C is the first one?
Yeah.
Oh, yeah, it does. Okay, so in that case, okay, so I got it wrong now. Yep, okay. Because the first operand is C, so C is the one that is getting changed, not D, which also means the next one is going to be off as well. It's going to be off by only just a little bit. It's going to be F8 instead of F9. But this one would just be saying unchanged. There you go. Okay, good catch, good catch. But that's kind of what I expect out of this particular trace. One student was very unfortunate because his A and B were really far apart, so it took that loop, like many iterations before he got out. But the student was, that particular student was actually observant and say, oh, this is a loop, then he just said, okay, do this like this many iterations and only this register get changed per iteration. I took it as a correct answer, because that clearly conveyed what the loop was doing to this code here. So do we have any questions about the answer of number 3? A little bit tedious, okay? So this year, I'm gonna change the format so that it is fair. Everybody has about the same length of trace. And then we are moving on to the last one. Oh, nope, second to the last. This is a floating point. We're gonna ignore this because we are not gonna have floating point numbers in this particular exam too. So now this is the last one, question number 5, which turns out to be my favorite. It's asking you to reverse engineer the following assembly code back into C code. So it's the reverse of the process. Be sure to identify control structures and signedness, if any, of the registers. Even though the registers are not inherently signed or not, the use of the values in the following code does imply whether they should be typed signed or not. When reversed to C code, note that the C code may not make much sense, but it should be structured, which means no go-tos in the C code, because otherwise the easiest way to do it is to have a whole bunch of comparisons and a bunch of go-tos and a bunch of labels. To reflect the original assembly language code, the C code cannot contain any go-to, break, or continue statements. So that was pretty clear. Okay? All right. So now the question is, how do we approach this? How do we get this started? And someone may say that, but Tech, you never taught us how to do this. And the answer would be, I never taught you exactly how to do it, but I gave you enough knowledge so that you should be able to do it. Okay? But now that we have this warning ahead of time, okay, let's try to figure out how to get this done. What do you use to recognize things? Well, the first thing I do is to look for loops, because loops really stand out. You typically have a label that is defined early, and then an unconditional branch or conditional branch in the case of do while that goes back to that label. Well, we found that, okay? So if you see a label at the beginning and an unconditional branch all the way at the bottom, most likely it is a while loop, okay? So I'm going to say, there's a while loop here. Okay. So once again, if you run out of space, you can use the insert symbol. But because this is the reverse process, the resulting C code is much more compact compared to the assembly code. So typically, you don't have the same kind of problem as when you're compiling. Okay. So now the question is, what is the condition to stay in the loop? So you have to be careful because the assembly code typically tells you when you should get out of the loop and not when you need to stay in the loop. So you need to kind of flip that logic a little bit. Okay, so the comparison, the out of loop label is L3. So now my focus is on L3. How do I get to L3? And I need to negate that condition to become the stay in loop condition. So I get to L3 if I get to this particular JZI instruction. So now the question is, how do I get to this JZI instruction to begin with? Well, if A is less than B, then I'm going to L2 and bypass going to L3 altogether. So one reason to stay in the loop is just A is less than B, unsigned, okay? So now I can say, I know A is less than B is a part of it. And I also know that A and B are unsigned. How do I know A and B are unsigned? It has to do with the use of JCI instead of JLI. If I use a JLI, then it is using the signed interpretation. If I'm using JCI, it is using the unsigned interpretation. Now JCI doesn't really reflect one way or another because it's the same, okay? But JCI versus JLI does tell me that information. Okay, so what if JA is not less than B? Well, if A is not less than B, then I compare B and C. If B and C are the same, I get out. So that means if B and C are different, I stay in the loop. Okay? So the stay in loop condition has involves B does not equal to, oops, that's not C. B does not equal to C is also a part of the condition of the loop. But now the question is, how do these two relate? A is less than B is one definite reason to stay in the loop. B does not equal to C is only evaluated if A is less than B is false, right? So should we use AND here or should we use OR here? We should use OR, okay? Because otherwise, if A is not less than B, we're going to get out. All right, so we have OR in here. So that handles the control structure of the while loop. So now my focus can now only be up to this here because that's the body of the loop. So this is also how I recommend you guys to do it, is to focus only on one level of logic at a time. Because if you try to look at all the code and try to figure out the entire thing all at once, it's going to be difficult, okay? So now I can focus my attention from compare AB all the way up to label L6. Because JMPI to L1 is a part of the loop, and that's already documented. Okay, so in here, I'm comparing, I have some conditional branch, but I don't see any branching back to an earlier label anymore. The additional branches, like L4 is a forward branch, L5 is also a forward branch. So I kind of guess that we don't have any loops. So if I don't have any loops, and yet there are conditional branches, well, I think we got a conditional statement, like an if statement, right? Okay, so we then put in the template of an if statement. And then I'm going to assume that we have a then branch as well as an else branch. Okay. If we don't have an else branch, you can just kind of leave the else branch empty. Okay, that's perfectly okay. All right, so now the question is, which one is the else branch and which one is the then branch? So typically the else branch is the one that is later, and then the then branch is the one that is earlier. So you have to look at code that actually has effect on registers instead of just comparing and going someplace. So the code that actually does have effect on registers is increment A in this case, and copy C to B in this case. Okay, so this is going to be my then branch. This is going to be my else branch. Okay, so we translate those two lines first. Increment A is going to go here, which is just A plus plus. If you write plus plus A, it's just as good. If you say A gets A plus 1, just as good. If you say A plus equal to 1, it's just as good. Okay, I just need to know that you understand how to translate it into one form of C code. Doesn't have to be the only form. And then the other one in the else branch is B gets C. Okay, like so. If someone gives me an answer of C equals B, I would deduct points, because that indicates that that person does not understand how CPR operates. Okay, so the syntax of the assembly code is important. All right, so now I just got the condition left to specify. If A is less than B, I go to label L4, which is the then branch. Oh, okay, that's easy. So A is less than B is the condition of the conditional statement. And we're done. Woohoo! So this is how we quote-unquote decompile a program. We look at assembly code which has no inherent structure whatsoever, and then we reverse it back to a form in C that actually has structure. Why do you think this might be useful? Because one answer is it's not useful at all. Tech is asking these questions just for asking just for the sake of an exam. Well, that's one way to look at it. Yep.
It also helps to, like, if someone were to hand you that, it helps you understand what exactly they're doing.
Yep. And under what situation legally would you have a need to do something like that? I have to emphasize legally, because in the United States, reverse engineering is actually illegal. Yep. But under what situation is it going to be like permissible, or you can apply for, I don't think it's called a license, but you can apply for permission to do it. I'll give you one example. You work for Caltrans, the Department of Transportation in California. Okay, so you look at you guys have seen people looking on those boxes, the controller boxes for traffic lights, right? So you open that panel, okay, those little shiny boxes, and there are circuit boards inside. I tell you, those circuit boards are really, really old. Okay, they're microcontroller based, so there's a processor and a program running in those things, but they're really old. Okay, nobody manufactures the processor anymore. No one even manufactures the components of those things anymore. If they break, there's no replacement. Okay, darn. So then what do? Well, you look up the internet and go like, oh, well, we got this Arduino board that has like 20 times the processing power of that little circuit board, that huge circuit board in the controller, but we need to replicate the logic exactly in order to get certified, so that the replacement circuit board can be considered equivalent to the original board. So what are you going to do? Disassemble the code and then decompile the program so that you can write the new code with an Arduino in C and C++. But it replicates exactly the same logic as the original code written in who knows what kind of programming language people used in 20 years ago. Do you see what I mean? Because you would still have access to the ROM of that component, but you probably would not have access to the source code anymore, because the programmer probably has passed away. 20 years ago, or some time ago. And the department has lost track, okay, of the original source code. So you don't have any original source code to begin with, and the only thing you have, to go with is the object code or the actual opcode in the ROM. So the first stage is not even this. The first stage is to look at a whole bunch of zeros and ones and disassemble the program. You look at a bunch of zeros and ones and go like, yep, well, according to that processor, this particular bit pattern means initialize register C to a value of 20. So you have to line by line, byte by byte, go through that painstaking process. There might be some programs that can help you with that process, okay, depending on how popular the processor is. But it is legitimate. This is a legitimate thing that people actually do in the field. Now, what about the illegal application of something like this? The illegal application of reverse engineering or decompiling. Why would anyone want to do something like this but have something bad in mind? Yep.
Because if you were to rip it open and figure out what it's doing in a hardware place, you could recreate it, and then there's no sign you've copied it unless they also go and double check both the sources.
That too. But let's say you want to run a particular program that is kind of expensive, okay? And you can download and install a demo version, but you cannot after 30 days it just goes like, well, if you don't pay and there's no permanent license and you cannot use this anymore, or they turn off certain features, okay? But those features are in the executable because you had access to those features during the trial period. So someone may decide, hey, if I can do something like this, I can look into the executable, find out how that code works, okay, how it checks the license, and then I can see if I can bypass that, or I can come up with my own quote unquote license, so that the program is happy and it will just give me full access all the time. You can kind of imagine how this can be used in that particular for that purpose, and only for that purpose is the reason why it is illegal in the United States, thanks to the DMCA. It's the Digital Millennium Copyright Act. So any attempt to circumvent copyright protection is by itself a crime. So even though you might be just doing research, never really use that approach to make money or to save money. You're just saying, okay, I actually bought this software fair and square. I am just curious of how the copy protection mechanism works. If you look into it and you share that result with anyone, you have just committed a crime under the DMCA.
Yep, it's about the same as hey, I found the bank security plan. Check this out. Even if you didn't have anything in mind, you just put their entire security plan in it. Or you told someone else about, hey, look, there's a blind spot.
Well, but if you think about it, is it really a crime? Because in the case of Microsoft, people have reported bugs in Microsoft Word, and I think Sony, got into trouble with the same kind of thing, where some legitimate user was reporting a problem that was totally legitimate, and then these companies look at that report of a problem and look at it through the lens of the DMCA and say, oh, this is bad. The EU doesn't have the same kind of rule, doesn't have the same kind of law. It's only when you perform the act of, in your example, breaking into the bank, then you have committed a crime. But sharing the information of how to break into the bank is not by itself a crime. Yep. It's a very different interpretation of what a crime really is. Is it the act of actually doing it, or is it the act of enabling other people to do it?
Because I'm pretty sure if I have the plans to a bank security system and I'm not employed by the bank, I'm getting held for questioning.
I think it also depends on whether you disclose that information only to certain individuals or you push it out on the internet. If you disclose it only to certain individuals, that can be considered a criminal attempt, okay? Because you're just giving it to someone else to carry out the crime, which you may benefit from the crime. But if you just push it out onto the internet, that means potential criminals and the bank have equal access to that information. Then the bank can also act on that information and protect and change the security means, right?
But then the question comes up of where you got it.
Sorry?
Then the question comes up of where you got it.
Well, you figure it out. There's no way to prove, whether I guess, if they find, illegal documents that you've, acquired illegally, from, the architect who designed the bank, vault to begin with, you can be faulted. But on the other hand, if you just kind of figure it out by yourself, there's no evidence whatsoever in your house or anywhere on the internet, they have evidence that you acquired that information illegally.
But when you're talking about stuff like
Yeah.
reverse engineered, like license protection,
Uh-huh.
even if I research that myself, that still means I went over into the back near the vault to like mark down for cameras or.
It depends on how obvious it is, right? I mean, you can be a legitimate customer, and you have your safety deposit box, and then when you walk past, the vault, you notice certain things that everybody else could see as well, but you deduced based on that information about certain flaws about that particular mechanism, and then you publish it. So, interesting stuff, skirting around the edge of what is legal and what is illegal, but I can tell you that the interpretation is very